Good morning. Today I would like to discuss about multiplication operation and division operations. How can we do using shifting? So binary shifting or binary data shifting on the registers. In previous class we observed the four categories of shift registers like serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out categories of shift register, their operation, and also we have seen the VHDL representation for serial in, parallel out shift register. And today how the multiplication and division operations we can perform using these shift registers. In this case, in order to understand these operations, here I am taking a 4-bit shift register with the data of 0010. Okay, let us assume we have a register of 4-bit size consisting the data 0010, that is binary value, its decimal equivalent is 2. Now if I shift 1 bit towards the left hand side direction, if I shift the data of the register in the left hand side direction by 1 bit position, the new data is like this: 0100, 0100. It is equivalent to decimal value of 4. So by one bit shifting towards left hand side, what we have seen here, the result is multiplied by 2 with the original value. So previously the register consists a decimal value of 2. Now it consists a value of 4. That is, by 1 bit shifting we can see a multiplication operation by 2. Okay. So similarly, if I shift one more bit towards left hand side direction, now what is that new data in the register? 1000. That is 8. Previously how much? 4. Now because of 1 bit shifting, okay, now the result will become 8. That is, it is 2 times of the 4. So like that, by 1 bit shifting towards left hand side direction, you may get a multiplication operation by 2. Okay. So similarly, for getting the division operation, the shifting is towards right hand side direction. That to division by 2 we may get. Okay. So let us see that one as okay. So for that one, so this is the, in this slide I am going to show that action, that is division action. So here also I am considering a 4-bit shift register, consisting initially the value of 1000. Now if you apply 1 bit shift towards right hand side direction, the new result is 0100. Actually the original value is 8, now it becomes 4. Decimal equivalent of original value is 8, now the decimal equivalent of the new value of the register is 4. That implies what? It is divided by 2. So 8 divided by 2 equal to 4. Similarly, if you do once again by right shifting, the result is 0010, that is 2. Therefore, the previous value is 4, now divided by 2 means the answer is 2. Okay, so like that, by doing the right shifting, you can observe a division operation. By shifting in the left hand side direction, you can get multiplication operation. Okay, so this is the way using shift registers how the multiplication and division can be performed. Now for the multiplication, here I am going to represent one VHDL program. Okay, so as you know already, while writing the program, first of all you need to open IEEE library. So library IEEE. Then use IEEE.standardlogic1164.all, that is the package. That is also you have to put in open mode from the library IEEE. Followed by this entity declaration. In the entity declaration, already you know, it declares all input ports and output ports of the digital system. Okay. Also here we can mention the data type for each and every port. Okay. So the syntax of entity is, it start with the word entity, then name of the entity. Here the name is PIPO shift register, that is parallel in parallel out shift register is. Okay. So using this parallel in parallel out shift register, you may have the multiplication and division operations. Okay. So this is the first line in the entity declaration. After that, so here generic of P2 colon integer colon equal to, that means Q2 is declared here. Q2 is an object. Q2 is an object which holds an integer type of data. That too, the value is 2. The value is 2. So the 2 is loaded in the P2 object. After that, the input output ports are declared. That is port of number. Okay, number is one signal variable, or signal object. It is input to the system, and it is declared in the form of vector consisting 8 bits, 7 down to 0. Okay, port of number colon in standard logic vector of 7 down to 0. So 8 bits it consists. The number is a signal consisting, or it has to hold 8-bit data. 8-bit data. That too, this is the input to the system. Next, MD. So MD is multiplication or division. This is also input to the system. Okay. So mode is in, data type is standard logic. That means it holds either a value of 1 or 0. Usually the binary values, we are using standard logic data type. So if the MD value holds logic 1, the operation is multiplication operation, otherwise the division operation. That is, if the MD consists 0, we can have the division operation. Okay, for that purpose this MD input is used. Then clock signal. So in order to get synchronized operation, the clock input also used. Okay, so clock in standard logic. Next one is final output is result, but result is declared in the in-out mode. That is, from the result you have to taken some bits and assign to the out number like that. So in-out standard logic vector of 7 down to 0. Standard logic vector 7 down to 0. That is, the output data also consists 8 bits. Both input and output numbers consist the 8 bits. Okay. Next, OVR, that is overflow. OVR is overflow. It is also output. Data type is standard logic, and initially it has to hold logic 0. For that purpose, at the declaration itself, I assign a logic 0 value to it using the symbol colon equal. Then this is the last signal in the port declaration. That's why closing parenthesis semicolon followed by end entity name. Okay, so what is the entity name? PIPO shift register. Okay, this is the entity declaration to our PIPO shift register to show both multiplication and division operations. Okay, so on 8-bit numbers. Remember, on 8-bit numbers. Okay, so the MD input value decides whether the operation is multiplication or division. If MD is 1, the operation is multiplication, and if it is 0, the expected action is division. Okay. So come to architecture body. As you know already, the architecture start with the word architecture followed by its name, that is behavioral of entity name before shift register is, then begin. Okay. So this is the first line, architecture, its name of entity name is. After that begin, because there is no declarations here, and the model here I'm going to write or represent the VHDL program for the shift register in the behavioral style. That's why the name given as for the architecture as behavioral. Then in the architecture model, behavioral architectural case, the statement is process. Okay, isn't it? In previous class we observed that in the behavioral model the preferable concurrent statement is process. Okay, so process of clock, that is whatever the actions done in the program, they are all with reference to clock. When proper clock signal is available, then only all those statements will execute, otherwise no. Okay, then process begin. As per syntax I am following process begin, then result equal to number, result equal to number. So in the result actually the output, number is the input. From the number input I loaded the result with the value of the number. So after that I am checking whether proper clock signal is or proper clock instant is available or not. Okay, that is, it is confined to positive edge triggering. Okay, positive edge triggering model. So that's why if rising edge of the clock, then whenever the rising edge of the clock is available, then only the operations, either multiplication or division operation, can be performed, otherwise no. Okay, so for that purpose we are going to check where is the clock instant, is it at rising edge or negative edge or some other place. Okay, so if rising edge of clock, then after that, suppose if the clock signal is at the rising instant, then you have to check MD value. Okay, MD value decides whether the operation is multiplication operation or it is division operation. Okay, so for that checking, if statement is used, if MD equal to 1, if MD equal to 1, that is multiplication operation we have to show. Okay, after multiplication, if overflow happen, that has to be loaded in OVR. OVR is the signal to hold the overflow. So therefore overflow is assigned with result of 7 minus P2 plus 1. That is, what is result of 7 minus P2 plus 1? P2 is 2, therefore 7 minus 2 plus 1, that is 5 plus 1, 6. So result of 6th bit, result is a 8-bit binary number. From that 6th bit value is treated as a overflow and is loaded in the VVR. After that, the result of 7 down to P2, that is 7 down to 2, is result of 5 down to 0. Okay, so in the result 7 down to P2, that means 7 to 2. The result of 5 down to 0 has to be shifted. Okay, and result of P2 minus 1, that is 1 down to 0, is assigned with the zeros. Okay, is assigned with the zeros. If you do the operations or the shifting operations like that, you can observe the result is multiplication. Result is multiplication of multiplication. Okay. And suppose if it is not, that is if the MD value is equal to 0, you can have the division. In division case, the shifting is like this. The result of 7 minus P2 down to 0 will be assigned with the result of 7 down to P2. That is right shifting. Right shifting gives the division operation. Okay. Similarly, the result of 7 down to 5 is assigned with zeros. Okay, this is totally right shifting action. Else part represents the right shifting. So for getting the division, whereas before else the shifting is left shifting, that gives the result of multiplication action. You can take one 8-bit number example and you can check out these shiftings and also check whether the multiplication and division operations you may get or not. Here I am not showing any example. You can try. You take one example 8-bit number. After that you do different shiftings, that is both right hand side and also left hand side as per these statements given, whether you can get multiplication and division or not. That you can observe, right? So this is the way how the multiplication and division operations can be done by using shifting techniques, and also here we have seen the VHDL program for the multiplication and division operations on 8-bit numbers. Okay. That too, here P2 value is the power of 2, the power of 2. With that power of 2, the multiplication and division can be done. Okay. So P2 value 2 means the power of 2, that is 2 square, that is 4. In both multiplication can be done 8-bit number into 4. Similarly, division also can be done with 8-bit number divided by 4. Okay. So P2 value, whatever the P2 value we have taken, it is considered as power of 2. Okay. Since here P2 is 2, power of 2 means 2 square. Okay. So that is the multiplication and division. Okay. Thank you.